Everyone. Welcome to our public lectures. I'm András Vasi, the chair of the math department. And I'm very glad that we have this occasion together here and that so many of you could come. Of course, we had a pause in our public events, but this is the third lecture that we have since the start of the pandemic. And it's great that we have this nice live audiences again. So our speaker today is going to be Leslie Lamport, who is going to talk about programming not being equal to coding. So let me just say a few words about him. So Leslie Lamport was an MIT math major, and then went on to do a PhD in mathematics at Brandeis. And he worked at various I think computer research companies, and then currently he's at Microsoft Research. He's been there since 2001. So he has received many honors. In fact, I don't know how many people have all these honors. Like he's a member of the National Academy of Engineering since '91. He received the IEEE John von Neumann Medal of 2008. He's been a member of the National Academy of Sciences since 2011. He received the ACM Turing Award of 2013. He's been a member of the American Academy of Arts and Sciences since 2014. So if you would like to know more about his work, since at least up till this Turing Award, the Turing Award citation, the Turing Award website, is actually extremely helpful. I definitely recommend this. Another very good source of information is his own webpage, where he has a part called Writings. And among other things, this is relatively early, not the earliest. He writes about his PhD thesis, which was about the analytic Cauchy problem with singular data. And so I'm a PDE person, so I actually looked this up. But he also says below it, the thesis itself was a small, solid piece of very classical math. Had Cauchy arisen from the grave to read it, he would have found nothing unfamiliar in the mathematics. So I think this is an understatement. Cauchy probably would have found some things unfamiliar, at the very least the way of thinking about things, even if, like if you go down to the trenches, at the end of the day, he would have been familiar with it. So in any case, after his PhD thesis, he continued very influential works in computer science, often related to distributed and concurrent systems with exciting names, such as the bakery algorithm and Byzantine agreement. So, but I should say that in science and math, probably what all of us know him for is LaTeX. So LaTeX typesetting is what most of us use on almost every day. And so tech was done by Don Knuth, who is also here in the audience. And so this is sort of macros and sort of packages on top of that. So we are all extremely grateful every day for all of Leslie's work. So with this, please welcome Leslie Lamport, our speaker.
Thank you, and I hope the computer will be rebooted and we can continue. Most excellent. Okay. Program is not equal to coding. Should we teach programming to kids? It's probably a good idea. Most people think that means teaching coding. Teaching coding instead of programming is like teaching typing instead of writing. Typing was one of the most useful courses I took in school. These days, I can't write without typing. But writing is a lot more than typing. You can't program without coding, but programming is much more than coding. So what is programming? Well, I'll be talking about simple programming. Writing a program that computes a value and stops. Excuse me. I don't have time to talk about more complicated programs, which are things I've worked on most of my life. But simple programming consists of three things: deciding what task the program should perform, deciding how the program should do it, and writing the code that does it. A metaphor: getting a robot to cook something. So writing cooking directions consists of deciding what dish to cook, choosing a recipe, and writing detailed instructions to tell a robot how to make it in your kitchen. So those detailed instructions might look like: take the green bowl from the top right cabinet, take 1 cup measuring cup from that drawer, and take a jar of sugar from up there, and fill this measuring cup from the sugar jar, and pour the contents into the green bowl, and so on. Now, these instructions are a lot more detailed and at a much lower level than the instructions in a recipe. Moreover, the robot doesn't understand English, so you have to write the instructions in a special robot language. Now, don't take this metaphor too seriously. Programming is not the same as cooking, and maybe you have a robot that doesn't need such detailed instructions, but I'm using the metaphor to explain my ideas, not to justify them. Now, a lot of programmers, I expect, will disagree with what I'm going to say, but I stand behind my ideas, but I'm not going to defend the metaphor. So let's fix the metaphor. Deciding how the program should do it. Every program does something different. Choosing a recipe, well, it's really inventing a recipe. So pretend we're inventing a new recipe every time we prepare a dish. Recipe books describe how to make components of a dish. For example, how to make a sauce. Now, 3 steps. Deciding what task the program should perform, deciding what dish to cook. Most programmers don't spend enough time on this, but I'm not going to discuss it. Now, writing the code that does it, or writing the detailed instructions for the robot, I'll have little to say about that. Deciding how the program should do it, inventing a recipe. And most programmers do this only while coding. They try to invent a recipe while writing instructions in low-level robot language. I'll show you what they should do instead. So how the program should do it, the recipe. I call this an algorithm. Now, that term is generally used only for the recipes that are in cookbooks. And those cookbooks are called algorithm textbooks when you're talking about programming. Now, the recipes in cookbooks are like the ones programmers invent, except that they can be used in making many dishes. Programmers don't realize that there should be a recipe or algorithm that their code is following or implementing. So I'm going to describe a simple recipe. Boiling water. Well, whoops, that's too complicated. Before you boil water, you have to put the right amount of water in the pot. So in our example, what I'll give is a recipe to put 2 cups of water into a pot using a 1-cup measuring cup. Now, at my age, that's the hard part of cooking, remembering how many cups did I put in there. So this is a really important program, algorithm. So I'll write the recipe as a flowchart. So we start with the pot empty, and here we execute the algorithm. And we keep track of how many cups of water are in the pot. We start out with 0 water, no water. And we start with executing statements at where this little token is, which starts at the top. So the first thing we do is add 1 cup of water. That adds 1 cup to the pot. There's now 1 cup in the pot. And it moves the token down to the next instruction, the next place in the flowchart. Then We do that instruction, add 1 cup of H2O. The pot now has 2 cups, and we're there and we're done. And the algorithm finishes with 2 cups of water in the pot. It's a correct algorithm. Now, this algorithm has other uses. I take 2 vitamin pills daily, and here's my recipe. Start with no pills taken. Each step I take 1 pill, and lo and behold, I wind up with 2 pills taken. Well, now let's act like mathematicians. Instead of pots and pills, we'll generalize to a variable x. So we start with x equal to 0, and each step is going to add 1 to x. So the algorithm finishes with x equals to 2, with x equal to 2. How do we know this? Well, we knew that by mentally executing the algorithm. I didn't have to actually go take water and pour it. We mentally executed it. But suppose the algorithm looked like this. An execution could take thousands of steps. We might be over here someplace and go around this loop a few times and then go someplace else and so on. And we can't mentally execute thousands of steps. So why does a correct algorithm produce the correct result? And what does correct mean? Well, we're just considering simple programming, writing a program that computes a value and stops. So correct means it computes the right value. So why does it produce the right value? Well, the answer was given to us by Robert Floyd, who was a Stanford professor. And he asked, while a correct algorithm is being executed, why will it produce the correct result? Well, because of what it did in the past? No. That's history. What you did 10 minutes ago isn't going to explain what you're going to do, how you take the next step. So it produces the correct result because of its current state. It's going to produce the correct result when it finishes because of its current state. So how do we express that in terms of our flowcharts? Well, we want x equal 2 to be true when the algorithm is finished, namely when the token is there. So when the token is there, we want x equal 2 to be true. Well, how do we make it true? Well, to make that true, when the token is at, I can't get that position. When the token is in the position it is now, x has to equal 1. So we want x to equal 1 when the token is there. And to make that true, well, if we're going to add 1 to x, then x has to equal 0 when the token is over there. And this, why is it true? Well, if you start with x equals 0, then that implies that x is equal to 0 when the token is, that means the x is equal to 0 when the token is on the first arc. So the algorithm produces the correct result because the formula attached to each arrow is true when the token is on that arrow. Well, the formula attached to each arrow is true. These are mathematical formulas. We understand the algorithm with math. So why does the algorithm produce the correct result? Floyd taught us how to answer this question with ordinary math. So we can use ordinary math to ensure that an algorithm produces the correct result. That's a wonderful contribution of Floyd. Another example. Suppose that we want a recipe for putting 20 cups of water into the pot. Well, we could modify this algorithm by adding 18 more boxes, but that's a lot of writing to do, and I can't quite fit it into the slide. So we'll look at a different algorithm for adding 2 cups of water. one that's going to be easy to modify for 20 cups. And this is it. You can read the flowchart, I think, and figure out, if you've seen flowcharts before, why it works. But let's execute the algorithm. We start with x equals 0. X is equal to 0. We put the token is on the starting point. We get to this test, is x less than 2? And it is, so we take that branch, the token goes on to that arc. We add 1 to x. Token comes around there. And then, once again, we execute that test. Is x less than 2? Yes, 1 is less than 2, so token goes there. Once again, we add 1 to x. Round it goes. And this time, is x less than 2? No, x is equal to 2. So we finish. And the algorithm finishes with x equal to 2, just like it should. Okay, so how do we show that it well, actually, if we want to add 20 cups of water, of course, we just change that 2 to 20. So, but we'll leave it at 2. So why the algorithm produces the correct result? It's because when the token is on each of those arcs, the formula that I added is going to be true. Well, why is that the case? Well, supposing we start here, well, it's true initially, because x equals 0 implies that x is less than or equal to 2. So when the token is there with x less than or equal to 2, and we execute that test, well, there are two possibilities. The first possibility is it is less than x than 2, in which case the token goes there, and x less than 2 is true when the token reaches there by result of the test. And the other possibility, that x is not less than 2, well, then we get to this arc. But this arc says x is equal to 2. It's true by the result of the test, which says that x is less than true, and the fact that when we started, x was less than or equal to true. So if x is less than or equal to true, and it's not less than true, then it must be equal to true. So it's true when it reaches, the token is true when it reaches, is on an arc whose formula is true if it reaches that no arc. And one other case to try, if we're on the less arc and the s arc, and we add 1 to x when x is less than 2, well, then we come around and, in fact, x is less than or equal to 2. Because if x is less than 2 and we add 1, then x is going to be less than or equal to 2. So that's true by that assumption that we start executing the box with x less than 2, and we add 1 to it. So when the token is on any arrow, the attached formula is true. Or is it? Well, let's try that again. Supposing the x is less than 2, well, supposing x equals 1.5. Well, x less than 2 is true because 1.5 is less than 2. We add 1 to x. We execute it. Then x gets 2.5. And lo and behold, we're on an arc where it says x is less than or equal to 2. But that's false because 2.5 is not less than or equal to 2. Should be, oh, there is a line there. So the algorithm produces the correct result, but these formulas don't prove it. Here's what does. We add to each formula the assertion that x is an integer. And then you go through and work it out. Everything works out correctly. And integer, of course, equals the whole number. So this works, but these are simple math formulas. What are these? It's got all this English in it. Well, This actually is a simple math formula, except I just wrote part of it in English. If we let int be the set of all integers, we can write that part of the formula this way. And is that funny sort of arrowhead symbol, and that epsilon means is an element of. So this is what the formula looks like when we write it in math. Now, maybe it's not true of this audience, but a lot of audiences see this. We'll start looking for the exit. Now, don't panic. If you're panicking, your panic is a problem that I'm going to get to later. And meanwhile, I'll stop writing those formulas and I'll write them in English. Now, let's return to our algorithms. Programmers would say this is just code. And they would write it more like this. This is how those boxes are written in code in most languages, these. And the programming language statement is written this way, means set the new value of x, the variable x, equal to its current value plus 1. They write equal even though it's obvious it doesn't mean equals, but programmers do some strange things. So, as I said, I've done most of my work on concurrent algorithms. So let's concurrent algorithm. My wife and I usually cook together. So we did an algorithm in which we each independently add 1 cup of water to the pot. Now, a concurrent recipe is one executed by multiple people, or an algorithm is one that's executed by multiple processes. So we're going to write it this way, where the one on your left is my process and the one on the right is my wife's process. So executing the algorithm, we start with x equals 0, and the tokens, now we have 2 tokens, one in each process. They start there. And there's one possible execution that I execute my add 1 to x box that sets x to 1. And next, my wife executes her add to 1 box. Token goes there, and x is equal to 2. And it finishes with x equals to 2. Everything is right. Here's the other possible execution, that my wife does hers first, and I do mine. And again, we finish with x equals 2. So those are the 2 possible executions, and they both produce the correct answer. Now, if I write this in Java, I don't expect anybody to understand this. I don't think I understand it anymore either. But this is what it would look like. And the problem is that in Java, these assignment statements, x equals x plus 1, x is assigned x plus 1. That Java program will actually finish with either x equals 1 or x equal to 2. It's not a correct algorithm. Why not? Because this Java statement, x equals x plus 1, actually represents a little program that's executing these 2 boxes. First, it reads the value of x, and then it sets the value of x to the value that it just read, plus 1. Okay, so if we executed this, my wife and I would execute this Java program, executing the algorithm, here's one possible execution. I read value of x. Then I set the value I've just read to that value plus 1. Well, I read a 0, so executing that sets x to 1, and it moves the token to the bottom. And then my wife will do the same thing. She'll read x, and she'll read x equals to 1. So she'll set the value of x to 1 plus 1, or 2, finishing with x equal to 2. But here's another possible execution. I read the value of x, and I see 0. Then my wife reads the value of x. She also sees 0. both processes, both of us have read 0. I now set x to the value I read plus 1, so I set it to 1. My wife sets it to the value she read plus 1, which is 0 plus 1 or 1, and she also sets it to 1, and we finish with x equals 1. So real code, like x equals x plus 1, is more complicated than this simple box that I just started with. But it's also precise. This is written in English. So here's how to write this in math so we can make that precise too. This higher level algorithm, which takes fewer steps, it is simpler, and gets the right answer. So here's going to write it in math. Write it this way, as x squared, as x prime equals x plus 1. So the x prime stands for the value of x after executing the box. This really means equals. It's not some funny programming type thing. This is a real math formula. Whoops. I'm sorry, something is... Ooh, how do I get back? Yeah, this really means equals. And somewhere I should have said the x without a prime on it stands for the current value. The x with a prime stands for the value after executing the box. And as I said, this is a real math formula. For instance, instead of writing it like this, I could have written it like this. It's an equivalent formula, mathematically the same. Or I might write it this way. If you try writing something that looks like that in Java, you get nonsense. So you can't manipulate code like you can math formulas. That's the beauty of math. So we can write our first algorithm like this. And we can also write this part of the formula in the box by adding a variable, call it t, which whose value tells you where the token is. So t equals 1 will mean that the token is on the first arrow, t equals 2 means it's on the second arrow, and t equals 3 means it's on the third arrow. So this formula, this flowchart, can be written as a formula. Here's the formula. You execute the first box, or you execute the second box. So executing the first box, what you do means that t equals 1, because the token has to be on the top arc to execute that box, and x prime equals x plus 1. And the token goes to the next box, where t is equal to 2, and t prime equals 2. So that execution of that box is described by this mathematical formula. Now, I've written an and in there, but you could replace the and by that funny caret sign, and you get an honest-to-God mathematical formula. Similarly, executing the second box is described by this formula. You start with the token t equal to 2, the token on the second arc, and so on, and finish with token equal to 3. So that explains that formula. Oh, this or, that's another mathematical operator that I've just written in English. So that formula tells you everything that's in that flowchart. And starting with x equals 0, well, that's already a formula. So these formulas, these mathematical formulas, describe this flowchart. So we don't need no stinking flowcharts. We can just use mathematical formulas. Oh, and also t equals 1 is also part of the formula that tells you how to start. So written as these formulas, And again, combined into they can be actually combined into a single formula, but I don't want to explain how, but that would take us don't have time. So writing algorithms as formulas. Now, I don't have time to explain all the things this makes possible. As an example, but what does it mean for one algorithm to implement another? Few programmers or even computer scientists know. You ask them, precisely what does it mean for a program to implement, to an algorithm to implement, one algorithm to implement another, or one program to implement an algorithm. They can't tell you. And the answer involves logical implication and substitution. And in fact, the statement that one algorithm implements another is expressed as a mathematical formula, which I don't have time to write. But these two very simple mathematical concepts, logical implication and substitution, substituting an expression for a variable, these are simple, basic mathematical concepts that underlie the meaning of what it means for one algorithm to implement another. And you can't express those in terms of code. There's no way you can say in code that that's true. So I'll have more to say about this later. And what about real algorithms? Programmers will tell you that math may be fine for toy examples, but it doesn't work for real algorithms. They're complicated. Real algorithms are complicated, and we need computer apps to check them for errors. That means that the math would have to be completely formal. And they'll say it's too hard to formalize real math. Few mathematicians would argue with that. I've asked a number of mathematicians this question. Starting with simple math, numbers, sets, functions, stuff you've learned in Math 101 or wherever. How long would a formal definition of the definite integral be? Now, the definite integral, that's the central topic of the second half of an elementary calculus course. Now, the answers I've gotten from mathematicians have ranged from a few pages to 100 pages. Except for one very smart mathematician, Cedric Vianney, who I just learned gave a talk here in 2013. He said 50 lines. But even he was off by a factor of 4. The answer is about a dozen lines of TLA+. Now, TLA+ is a language for doing simple math, plus a little bit of notation used for writing algorithms, for example, the prime. And there are computer apps for finding errors in algorithms written in TLA+. TLA+ is used in industry. For example, here's a paper that was written by a bunch of people at Amazon Web Services. That's the people that build Amazon's cloud structure. And this, how do Amazon Web Services use formal methods? And the formal method they used, and they're talking about in the paper, is TLA+. So this, in the small print, are their key insights. Formal methods find bugs in systems designs that cannot be found through any other technique we know of. Formal methods are surprisingly feasible for mainstream software development and give good return on investment. These guys are hard-headed engineers and business people. They don't do something if it doesn't pay. And at Amazon, formal methods are routinely applied to the design of complex real-world software, including public cloud services. Formal methods find bugs in system designs that cannot be found through any other technique we know of. Well, what they're saying is it's not formal methods that do magic, it's math that can do that. And there are lots of methods for finding coding bugs. They're not good for finding subtle bugs in system designs, another name for algorithms. So, writing algorithms in math. The formula describing a real algorithm can be hundreds of lines long. You can't write long formulas in English. Instead of writing, this, and x is an integer, we've got to use nice compact notation. And we've got to learn to use it. But people will think that a 100-line program is simple, but a 100-line formula is impossible to understand. They think, an x program statement, x gets x plus 1 is simple, where x an element of int is hard to understand. Well, they've got it all wrong. It's this that's hard to understand. Why? And this is easy to understand. Well, why is this hard to understand? Well, just this part of it. I won't even talk about all the complexity involved in what that assignment actually means mathematically. Just x plus 1, 3 plus 1. What does that mean? Well, it's the number of things you get if you take 3 things and add 1 more thing. What does 3 things mean? What does 1 more thing mean? To understand 3 plus 1, you have to know how to count. And how many years does it take a child to learn how to count? But this, x, an element of int, is really easy to understand. What does this formula mean? It means that int is a bunch of things, and x is one of those things. You can explain it to a child in a few minutes, even with pictures. Here, this means that this person is one of these people. You can explain it, to a second grader. That's easy to understand. So why do people look for the exit when they see it? And it's not just, just not you, or these are programmers and software engineers who look for the exit when I start writing formulas. Now, caution, metaphor ahead. Math is a non-native language. To be fluent in a new language, we have to learn to think in it. Mathematicians are fluent in math. They think in things like, in formulas like that. But they write x as an integer. When you look at it, even in a math textbook, you won't see x element of int. People will say x is an integer. They may teach grammar and vocabulary, for how to write that. But they don't teach students to think in simple math. They had to learn it themselves. Now, the Whorfian hypothesis. Benjamin Whorf was a linguist, and his hypothesis is that the language we speak influences what we can think. Or the language we think in influences how we think. So we think only a little bit differently in French than in English, assuming we're fluent in both. We think a bit more differently in Japanese than in English, assuming, again, we're fluent in both. We think a lot differently in math than in English, if we're fluent in both. Not being fluent in math is a handicap for programmers. Here's an example. Rosetta was a spacecraft from the European Space Agency, and it explored a comet. And some of the instruments on it were controlled by an operating system called Virtuoso. The next version of Virtuoso, they decided to start from scratch, and they first wrote a high-level design in TLA+. Here's what Erik Verhulst, the head of the development team, wrote to me in an email. I had nothing to do with this. I just found out about it when somebody told me about the book. He wrote, "The TLA plus abstraction helped a lot in coming to a much cleaner architecture. One of the results was the code size is about 10 times less than in the original version. 10 times less code. You don't produce 10 times less code by better coding. You do it with, he said, a cleaner architecture. I would say a better algorithm, which comes from mathematical thinking. He also wrote, we witnessed firsthand the brainwashing done by years of C programming. It's a popular programming language. Well, it's not, it's a coding language. I don't call these things programming languages because they're not all about programming, they're just about coding. First hand brainwashing, I would call it mental impairment. It's the Whorfian effect on the brain of a language that restricts your thinking. The result of thinking in code instead of in math. Now, C is one of many coding languages. They all have their proponents and their detractors. As I said, this part of programming, writing the code, I'm not going to have much to say about it. And I'm not interested in what coding language people use. Remember, algorithms written as flowcharts can be described with math. In the same way, code can be described with math. It's called giving a semantics to code. Semantics is a way of saying giving a meaning to code. And Floyd's original paper was titled Assigning Meanings to Programs. Assigning a mathematical meaning to programs. Writing algorithms as formulas. As example, what does it mean for one algorithm to implement another? Few programmers or computer scientists know. And the answer involves logical implication and substitution. Now, you could write code as well as algorithms as formulas. And what does it mean for another algorithm, one algorithm to implement a program? Same thing as what it means for code to implement an algorithm. Again, few computer scientists or programmers know. But if they don't understand what it means to code an algorithm, what it means for their code to implement an algorithm, how can they do it correctly? And the answer involves logical implication and substitution. The way to understand it is to think in math. Now, writing codes as formulas, in the metaphor, it's this part, detailed instruction to tell a robot what to do. You know, a whole bunch of stuff. Code has lots and lots of details. And the formulas that describe the code are very, very big. And they're almost never written in practice. But understanding how it can be done lets programmers understand what it means for code to implement an algorithm. And that understanding will help them do it correctly. It's not going to eliminate all coding bugs, but there are lots of tools that are good at finding coding bugs. They're not good at finding algorithm bugs. So code versus algorithms. I've talked about two kinds of languages, an algorithm language, TLA+, and a coding language like C. Now, there's actually a spectrum of languages. They range from the lower level code language to the higher level like TLA+. So you can range them by level like this. And the lower level ones are less expressive. The upper level ones are much more expressive. And they can express things much more compactly because they're so expressive. But the higher up you go, the less efficient it is to execute it. So where you put language on this rainbow depends on the criteria you use, more expressive or not, the kind of program you're writing, and personal preference. Code meant to be executed, algorithm, usually translated by hand into code. Usually, I've actually written some programs, some little programs in TLA Plus, and executed them with the apps that are usually used for debugging. It's a great way to program if you're willing to give up 1,000, multiple of 1,000 in execution speed, which for the little problem I was doing was fine. But basically, there's a line between, what you can execute and what you can't. And now, it's translated by hand to code. In the future, the translation can be done by AI to code. And that future is coming fast. So the line between, what, can be compiled into, to the computer and, the algorithm language is getting higher. But that top is math-based. And I think that, sorry, I can't go backwards on this. Oh, yes, I can. I still think, in the foreseeable future, we're still going to want this very high-level abstract design that we can think about in math. We're not going to let the, we're not going to talk to the computer in English because English is imprecise. And if we talk to the computer in English, we're never going to be sure what it's going to produce. So should we teach programming to kids? It's probably a good idea. But we shouldn't teach only coding. Most of today's coding is going to be made obsolete by AI. We should use programming to teach kids simple math. Math is not going to become obsolete. Kids are better than adults at learning a new language. They can become fluent in simple math, and that fluency will last all their lives, and they'll become fluent in more and more math as they go. But they got to start young. And the way to become fluent is being taught to use the math, not just to solve some dull problems by rote. Man, the simple math is simpler than code. If kids can learn code, which, they do, they can learn simple math if teachers can learn to teach it. Can teachers teach it? I don't know. I'm not a teacher. But the first step is for computer scientists to learn it. So then they'll be able to teach the teachers. But they're going to have to overcome the brainwashing due to years of coding. Mental impairment. They have to learn that programming is more than coding. Programming is designing an algorithm and writing code to implement it. They'll have to learn to think mathematically about algorithms. Computer scientists and programmers can learn how, if they want to, by searching for TLA Plus on the web. I'm not saying it's not great. It's not the best way. I wouldn't use it for teaching kids math. But I think for people who, grown-ups who learn to program, it's a pretty good way to get them to start thinking in terms of math. You can find it on the web. Thank you.
Thank you very much for this very nice talk. And so there are questions or comments. Please go ahead.
Well, I think by computer-based math, I think what you're saying is that you can use the computer to do math for you, but you have to give the computer the math. Now, right now, they're giving the computer the math on, I don't know what's going on in school books, but it's always, Jane has 3 flowers and, something like that. Maybe the math can be, we wanted this program to do this, and explain that mathematically. So yeah, I mean, these are complementary things. They're not, one or the other. Or could you?
Sorry, could you repeat this again? Slowly.
Good. Oh, great.
Hey, hello. Yeah. So thank you. So first of all, thank you for the talk. So what I'm saying is, we are in Silicon Valley where we are known for making money out of technology more than being, well, we do both, but that's what we are known for. And in the marketplace, you mentioned the example of Amazon, but you've spent a lot of time with ESA, which is they have a lot of time to plan their projects for 5, 10 years. In Silicon Valley is the land of startups where there is the time frame between idea to product is very short. So how do you apply your ideas to the Silicon Valley ecosystem of being as fast as you can?
Well, if you're saying people in Silicon Valley want to, hurry up and produce, buggy code, and they'll make more money doing it than producing, correct code that will, non-buggy code that will take longer to produce. Well, Amazon or Microsoft, Azure and their Azure system, they know that, their customers are depending on the correctness of their systems, and that, a bug in their system can mean that some company, either, is offline for a long time or loses their data. And they're not going to be making very much money if they keep losing people's data. So right now you can, in fact, that's the thing I've observed, that's things that happen as a result in cloud computing and large-scale computing, is that engineers who thought, oh, we'll just do some testing, and that's good enough, they no longer think that way, because they understand that, their customers are depending on them. We're still relatively young in the computer age, compared to, other things. And people, people are going to start paying attention to programs that are buggy. And they're not going to want, they're going to be able to start telling the difference between lousy programs and good programs. And it's going to, I hope, get more people to, more programmers to be thinking about, quality. But also, I should also say that there's nothing in thinking, basic idea is thinking before you code. And the option is not thinking. And not thinking is never a good idea. So it's really, you have to make sure it's a difference between how much thinking you're going to do, than how much thinking you need to do. And people, often learned that, rushing things and not thinking costs them more time in the long run. I've seen that happen. And I've seen the converse happen where, project, people spend a lot of time thinking and people are worried, oh, they're not producing code, but they then start producing the code and they can produce the code quite rapidly. I know that I save myself a hell of a lot of time by thinking before I start coding, from writing something for my own benefit. And the advantage that I find is that by thinking hard about what it is that I actually want the program to do, I can realize that what I needed to do can be a lot simpler than I thought I had to do. And making something simpler is a lot faster and easier than making something more complicated. So, not thinking is not a great recipe for saving time.
So the microphone's now set up, so please go to the microphone so the speaker can hear you better. Yeah, so please go ahead.
Hello. Thanks so much for this wonderful talk. And I just wanted to ask you about your thoughts, maybe a little bit more technical. There is this Curry-Howard isomorphism about bridging the gap between maybe math and programming. And then we also have dependently type theories that kind of implement all these formalisms. Can you...
I'm sorry, I'm having trouble understanding you.
What I'm saying is, what are your thoughts about using the language of Curry-Howard isomorphism and dependently typed theories to implement thinking mathematically about programming?
There's something in the acoustics here with that mic that's
okay.
making it hard.
Let me try.
It sounds like it's too technical a question for even me to answer. I mean, Curry-Howard is something I haven't thought about in 30 years. The math, I explained it to engineers. It's really simple. Any mathematician looking at it would say, what's the problem here? You don't need anything as fancy as Curry-Howard isomorphism.
But could you say that the typing theory is something that we should teach, like types?
Types, oh, yeah, actually, yeah. Types are great in programming languages. I love them. Types are lousy for writing the high-level algorithm descriptions that we use. Because the math is so simple that, you see, when mathematicians do math really formally and really complicated math, they need types. I won't go into the reason why. But the math because the engineers aren't doing deep math, it's broad, a lot of details, but very little depth. You don't need types, and types basically make it more complicated, makes the language more complicated and less expressive. And so TLA plus is on type.
Okay, thank you.
Yeah, hi, I'm Dhaval. I'm a computer science alumni here. The question I had is, you mentioned about English language, not a good way to specify into AI and programming because of ambiguity and a lot of other reasons, obviously. What are your thoughts on well-written design and functional specifications and languages like Sanskrit, which are quite mathematical?
I don't know transcript. I know there have been various languages that are sort of put a veneer on math and sort of let you write precise formulas in English sentences. And well, personally, I've never found them attractive, of course. Having been educated as a mathematician, I wouldn't. But I think even people, why bother learning this particular language for expressing the math. Why not use the language that mathematicians have developed for over centuries?
And what about well-written design and functional specifications as part of the software development life cycle? We already do that. So maybe that can be an input into AI to create programs versus math.
Okay, well, when you talk about functional stuff, basically when you're talking about functional stuff, you're generally talking about traditional programs, what I call programs that are basically, computer value and stop. And they, what you've learned for those programs does not transfer to concurrent programs and concurrent systems.
Okay, thank you.
Yes, thank you very much for the talk. I'm a GSB alum from a long time ago. And back here, my wife is a daughter at the hospital, and not daughter, doctor at the hospital. But I followed your work for some degree of time. I think that the most challenging thing to me, I'm originally from West Virginia and Western Pennsylvania. Nobody understands what you're talking about. How, or what I'm talking about. How do we convey that to people who understand that it's not as though coal mining and steel mills have been left behind? We're not just throwing people under the bus. They're just complete new technologies. How do we convey this to average people from a political perspective, social perspective? I mean, you mentioned, for example, the thing that was most interesting to me was just teaching basic math.
Yeah. You're asking a question that's, I don't have answers to it. It's not my, my field. I'm, trying to teach engineers to think about, the way I think, because I've found that to be a very useful way of thinking. But it's for, what this means to, people who aren't writing programs and stuff. That's I have nothing to say about that.
Hello, brilliant lecture. It has been my experience in dealing with non-mathematicians that, for better or for worse, people are drawn towards concerns of practicality.
I'm sorry, it's concerned with what?
Concerns of practicality. Yeah. People want to learn how to drive the car, not how the car works. So, from your career, do you have any lessons for how to convey to people the significance of mathematical thinking, given that our civilization is at a point where we will have as great a need of mathematicians as we ever have?
Well, if reducing the amount of code in your program by a factor of 10 doesn't sound like a practical thing, what can I do? What can I say? By the way, I should say that most, that's a very special case. And the reason it's a special case is that particular use of TLA+, they started right at the beginning to use, to design in TLA+, and that's how they got that factor of 10. Most uses of TLA+ are used for designing a specific algorithm that's part of a larger system, and they're just trying to get that particular crucial algorithm that involves concurrent synchronization right. And so what they'll see is, they'll catch bugs, but they're not going to make a large difference in, the amount of code that's going to result in that is actually a product of what they're doing is very small compared to the size of the system.
Thank you.
Hi, can you hear me? I have a two-part question. The first part's a little boring. Just curious if you've heard of Lean, the programming language. It was created by a guy, Leo de Mora, who is formerly at Microsoft Research, but now at AWS.
Okay, answer quickly, no, because I don't pay attention to programming. It's a coding language, I presume.
Well, it's gotten a lot of attention in the mathematical community. There's actually a thing called the natural number game that teaches kids how to prove certain things about the natural numbers. Terry Tao is formalizing a paper in it. So just curious, kind of, I think it would be good to look at because it's getting quite a bit of traction, and you might want to point people to it instead of TLA plus.
Well, I don't know that. I mean, first of all, whenever I say every programming language designer says there's no need for a specification because it is so clear from the code what the program is doing. The first language that they've said that about was Fortran. So, no, I think I've not seen, any language that, as I pointed out, languages are moving up in that spectrum, but they're still, still far away from being able to either write things at a high enough level of abstraction or produce efficient enough code. The foreseeable future, we're going to need basically math in a language that we don't know how to compile.
Can I ask the fun part of my question?
Yeah.
What makes you, so if you're confident coding will be replaced by AI, what makes you confident math will not be?
Well, remember, remember the first part of that, of the 3 steps. I've been talking about how the program works, but there's also the step about what the program does. Now, what the program does, what we want the program to do, it's human beings who decide that. I hope that the computers are not going to be telling us what we want. And so we're going to have to translate the what we want precisely enough that the computer will be able to do it. And so, and that has to be, something like math. I don't think I have anything, more to say about that.
Oh, thanks.
Oh, hi. First, thank you for the talk. So you mentioned a lack of skill in teaching computer science in K through 12. Is there anything you'd like to see changed besides implementing more math and coding in this field?
I don't know. That's a very open question. I mean, what I like, I can't come up with a coherent answer to something that vague. I'm sorry.
Oh, I have one more question. What was something you'd like to know when you started learning math?
Something I would like to know when I'm starting math. Well, okay. One thing I can say is that when I learned calculus in high school, there's a very nice book called by Thomas. I think it's actually still in print. It proved everything except what the the integral of 1 over x. And it wasn't until grad school that I learned how to prove what that was. And so that's all I can think of.
Thank you.
Thank you for your talk. I was also curious more about your thoughts on education. Specifically, how do you think more mathematical thinking, more programming thinking can be integrated into current approaches to teaching kids programming, like Code.org, Scratch, Lego Robotics, these things?
I'm sorry. Teaching is not in my area of expertise. So that's what I said. Can we teach teachers to teach it? And I don't know. So,
That's fair.
so go for it.
I'll keep thinking about it.
Compared to Lisp, how does TLA plus like jibe like with being high level?
Well, Lisp is a coding language. Actually, yeah, funny, when I actually started, when I first learned to program in, when I learned to program in Lisp, people said to me, oh, well, you're a mathematician. I was, a grad student at the time. And so you'll have it's an easy time. And I didn't have an easy time. I had trouble with it. And now somewhat later, I realized the things that I always had trouble with was a val and quote. And there's nothing like a val and quote in math. Now, if you don't know Lisp, that will mean nothing to you, but if you do, it will be the answer. So, Lisp is, maybe fine, it has some nice things, but it is a coding language, not math.
Thanks for the talk. So as you mentioned, we should try to convey our ideas through math instead of English, as it's more precise to like AI agents. And my question is, since nowadays people don't really like convey their ideas through math, so it's really difficult for us to get training examples to train AI agents like that. Like most of the agents are still trained on English. Oh, well, I don't know. I mean, I know next to nothing about AI. And there's actually, there's been a little use of AI and, it's a Microsoft Copilot where, it's not thinking for you, but it's helping you to, to write. And that's been, some use of that, so to simplify, to help people write their TLA plus specs, but so apparently it can be done, but I don't know anything about it.
Thank you so much for your talk. My question is, what kind of math would you recommend one to learn to better think in terms of mathematics? Because I think your examples have elements of real analysis, and a curriculum here at Stanford for computer science has discrete math, logic, and probability, which are all very practical. But I wonder if there's anything specific you think one should learn.
Well, I mean, things that you need to know. I mean, you need to understand basic logic, propositional predicate logic. Simply, that's pretty much, like the learning to spell in math. Very, very basic set theory. But other than that, that should be a foundation on which whatever math you're doing is based. And I think, the subject matter is less important than how it's taught in terms of learning to say things precisely. But without going into particular examples of stuff, I can't say anything intelligent, I don't think. But basically, the idea of there's a way of well, the basic thing I think that I haven't mentioned, but is really very, very important and has been crucial to my career, is the ability to abstract. And if the idea can be brought across of how mathematics is using to simplify by abstraction, that would be a great thing to teach. But how it's done in any particular subject